and its applications. Okay, so what is the Jacobian? So let's say that we have, let's say we have a function, say f, and that is really composed of many other functions. So let's say f1q, f2q, f3q, and so on till fmq. Okay, so it's a function of functions. Here q is the independent variable, and that's say x1, x2, x3, and so on till xn. Okay, so given this, we can define the Jacobian to be as the partial derivative of f with respect to q. So what will that be? Well, it will be something like this. tf1 tx1. Well, so by the way, another way of writing this is d f1, f2, so on, fm, dx1, x2, and so on till xn, which is the same as doing partial of f1 with respect to x1, partial of f1 with respect to x2, and so on till we end up with df1 dxn. And we do the same thing with df2, so on till df2 dxn, and then just keep going all the way till dfm dx1 dfm dx2, and so on till dfm dxn. So this happens to be a matrix, and you can see that this matrix has m rows, because you go f1, f2, f3, and so on, fm for the rows. And then if you can see that we go x1, x2, x3, so on, till xn for the column. So it's a m by n matrix. Okay, so let's see how to apply this. Here's an example. Let's say I give you f as x squared plus y squared and 2x plus 3y plus 5, which are basically the two functions, f1 and f2. Clearly, the q over here is x and y. And so if you're supposed to find the Jacobian, it's going to be df1 dx. Let's see, this is f1 f2. So df1 dx, df1 dy, df2 dx, df2 dy. And so when you take the partials, you get derivative of f1, this term, with respect to x. So again, when you take the partial derivative of x with respect to x, you treat y as a constant. So this one will be 2x. And then if you want to take the partial derivative of f1 with respect to y, you treat x as a constant, so it will be 2y. So next we go to line number, row number 2. So we do df with respect to x, df2 with respect to x. So here we treat y and 5 as constants, so we have 2. And then when you take the derivative with respect to y, we get 3. So that is the value of the Jacobian at a generic point x comma y. If you want to find at a specific value, let's say 1, y equals 2, you just put x equals 1, y equals 2, and you get j equals 2, 4, 2, 3. So that's the Jacobian evaluated at the point x equals 1, y equals 2. Now, if you're going to do this with MATLAB, it turns out there is a simple way of doing this. In MATLAB, what you can do is you can define Jacobian to be, it's actually a command called Jacobian or function called Jacobian, because as Jacobian f comma q, where you would obviously define f appropriately and q appropriately, and you would get the value of j. So this is symbolic, that will give you a symbolic value for the Jacobian. You could also find uh, the numeric value by, well, one is subs. So let's say this J1, so J symbolic, let's say JS, J numeric is, you'll take JS and then you'll put the value. So in this case, 1, 2, and then you'll get the numeric value of the Jacobian. You could also use finite difference, just like we use finite difference to find the derivative, right? We just take a perturbation in the x direction, perturbation in the y direction, and take the appropriate difference to find that. So that will be something like this: delta f, delta x, so delta f1, delta f2, delta f1, delta y, and then delta f2, delta x, delta f2, delta y. So you literally take delta x, put in the value and get it. So if you want to expand this, it will be something like x plus delta x, f1 x plus delta x y divided by delta x, f1 x is constant y plus delta y, and the same thing for y, and then you can basically find the answer to, sorry, I'm doing a mistake here. This should be, I'm out of space here. Let me just rewrite this. I'm missing that minus term. So let me just write it again here. So this will be f of x, f1 of x1 plus delta x comma y minus x comma y divided by delta x, and then f1 x comma y plus delta y minus f of x comma y divided by delta y, and the same thing for y. And then you'll have the derivative. So you'll have to do a few evaluations, that is, evaluate f at x plus delta x and y plus delta y, and then put the value. So I'm going to show you how to do this in MATLAB. Okay. So I'm switching computers. I'll share later on, but essentially I'm solving the same problem here, which is I need to find the Jacobian of the function which has x square plus y square and then 2x plus 3y plus 5. I just packed it up in a function, fn, which is f, and it has two parts to it. There's an f1, and then f2. Okay, so it just basically returns me the value of f. Okay, and this is actually a symbolic one now. Okay, so I define x and y to be real. My q, which is actually q, and then q0, q, I should have put q everywhere to be consistent with my notation. Okay, so first this is q, x comma y. q0 is a particular value for x comma y that's going to be 1 and 2. And then what I do here is we just go one by one at a time. Let's run this. Okay, so this is basically running the command f Jacobian f comma q. It gave exactly the same result. If you want to find the symbolic value or the numeric value, by putting in the value of q, that is x comma y with 1 comma 2, then you get 2, 4, 2, 3, like I showed earlier. And then this part of the code is slightly more involved, which is basically I wrote my own function Jacob, which uses finite difference. Okay, and let's run that. So you can see that the Numerical evaluation using the symbolic derivation gives me the same answer as the numeric value. Uh, this part is the one which I wrote down. It's a little bit involved, but I did not actually use Euler's method, which I showed in my notes. I actually used the central difference, and the central difference I need to do plus minus. Basically, what this means is the Jacobian here was something like this. You do f1 x plus 2 delta x dx y, and then you do minus f1 x minus dx y, and you divide the whole thing by 2 dx. Okay, so that's how you get the value for the first term. And then if you want the second term, there's the first or second column, then you just do the same thing in the y direction. So this needs to go here. Plus dy, and then you divide this by 2 dy. And the same thing will be applied to um, the second row and so on. Okay, so that's what I did here. It's a little bit involved, but if you follow through this, you'll see that it's pretty much what I wrote down here. Okay, so that's it. Let's now go to some of the applications of the Jacobian. Of the Jacobian. Okay, first one is finding velocity. Okay, so we've seen that. So this is the sort of the short derivation of how to find the velocity using Jacobian. So what we've seen so far is that the Jacobian is df dq. Okay, this is the definition. Now, if I'm given a position vector r of a point, and that position vector is basically some function of q, right? Example, you can say that x equals L cosine theta. See, that's the x position of the center of mass of a simple pendulum, right? Now, let's take the Jacobian of this. So that's going to be dr dq, which is df dq. Okay, and that's, we know, is the Jacobian. Okay. So we can write this as dr equals j dq. We can divide by dt and sort of replace the partial with the complete derivative. Then we get dr dt and take dr dt to start with. Okay, and since basically r is going to be only a function of this, time is not explicitly show up here, you can actually replace the partial with the complete derivative. So you can write this as dr dt equals j dq dt. In other words, r dot is jq dot, and this is, so to say, the expression we are after. That is, we find the velocity of r, or sorry, the rate of change of r. R is x, y, as the Jacobian times q dot. What is q? Q are the degrees of freedom. So in this case, for a pendulum, it's going to be thetas. Okay, so let's see. That's a derivation. Let's see how to use this. Okay, and I'll go back to the double pendulum we talked about. So example. Double pendulum. Okay, so the double pendulum I've drawn so far looks like this. This angle is theta 1, this angle is theta 2. And there's a center of mass, it's called that G1. There's another center of mass called it G2. This point is P, and this point is Q. And if you like, there's gravity. Okay, so then what we can do is we want to find the velocity of point G and G1 and G2, and we need the velocity because we're then going to use the expression for the Lagrangian, which has the kinetic energy, right, to find the equations of motion. So we need the velocity of G. So what we can do here is we can write the velocity of G1, which is, by the way, d of r dt. R is here the position of G1, is the same as the Jacobian of G1, and I'll define that in a bit, equal times q dot. Okay, so what's q dot? Q is, in this case, the degrees of freedom. In this case, the degrees of freedom are theta 1, theta 2. And then to find the Jacobian, we need to find the position of point P. So, or position of G, sorry, G1, sorry, it's going to be, in this case, well, you could use the fancy translation rotation formula I wrote down, or you can just do that by inspection. So if this is the x direction and the upward direction is the y, then just by inspection you can see that the position of G1 in the x direction is going to be, so given that this is C1, it's going to be C1 sine theta 1, and then the y coordinate is going to be C1 cosine theta 1, and I believe we chose y to be up, like, yeah, so it's going to be negative. Okay, so that's negative cosine theta 1. Okay, with that, let's find the derivative. So Jacobian of G1 is going to be dr G1 d q. So I need to do is d, so let's call this, if you like, this is xg1, yg1. So all I need to do is dxg1 d theta 1 dxg1 d theta 2 dy g1 d theta 1 dy g1 d theta 2. Okay, so that boils down to the derivative of this with respect to theta 1 is going to be c1 cosine theta 1. The derivative of G1, which is again this thing, with respect to theta 2 is going to be 0 because there's no theta 2 appearing there. Then we need to do derivative of y with respect to theta 1. So derivative of cosine theta 1 is minus sine theta 1. So it will be C1 sine theta 1, and then the second part will be 0. So that's how we get JG1. So if you want to find VG1, it's going to be C1 cosine theta 1, C1 sine theta 1, 0, 0 times Q. Q is, well, in this case, Q dot. The Q dot is going to be the rate of change of Q. So that's going to be omega 1 or theta 1 dot and omega 2. And so our answer is going to be C1 omega 1 cosine theta 1, C1 omega 1 sine theta 1. Okay, this seems a bit lengthy if we need to do it by hand, but because of the command Jacobian f comma q in MATLAB, this actually is much simpler to do it in MATLAB than to do it by hand. Okay, so is there one Jacobian? No, the Jacobian is actually you can find Jacobians for anything. So here I wrote the Jacobian for position G1. I can write Jacobian for G2, which I'm going to do in a bit. You could also write a Jacobian for the point P and so on. Now there's something else, which is the constrained Jacobian. Okay, so this is something which will come up a little bit later when I actually derive the equations of a legged machine. The constraint Jacobian comes where you want to enforce constraints. So, for example, if in this case I wanted to change this problem to the double pendulum and make it a loop constraint, in the sense I want to fix this point Q to the wall. Okay, now that's a bad idea for this particular thing because it becomes a rigid structure. But imagine that this was like a 10 link pendulum, and the 10th link, end of the 10th link, I wanted to constrain it to the wall. Then what I need to do is I need to ensure the constraint is satisfied. It says that the end point, that's Q, should be over here. And then you write the position of point Q, then you take the derivative of that Q with respect to degrees of freedom. That becomes your constraint Jacobian. And the reason why you want to find the constraint Jacobian is because that Jacobian is then used with the Euler-Lagrange formulation to basically enforce that there's a loop closure. And this is something which, again, I'll get into a little bit more details when I do Legged machines, because that's where the constraint Jacobian is, some manifestation of the constraint Jacobian is used. Okay. Okay, so that's the velocity of G1. We can also write uh, velocity of G2, which is basically J G2 Q dot, okay, where this is going to be dx G2 d theta 1 dx uh, G2 d theta 2 dx, sorry, dy G2 d theta 1 dy G2 d theta 2. So then I just need the positions of point G2, right? And G2 is the center of mass of the next link, and that something which you need to write, which I believe I wrote down in one of the classes. So y or x G2 is going to be, I think it's going to be L. We can just look at it from the geometry. So if I want to find the position of G2, it's going to be L, which is the length of the pendulum. I think I wrote it as L. And then let's say that this is C2. So you can see that the x position of G2 is going to be L sine theta 1. And then you'll have to add on to it C2 times sine theta 1 plus theta 2. So L sine theta 1 plus C2 sine theta 1 plus theta 2. And then you can similarly write yg2, it's going to be minus L cosine theta 1 minus C2 cosine theta 1 plus theta 2. And then, of course, you can then use this to find velocity of G2 based on the formula I wrote down. So I will not write that down because there's no point really writing in a lengthy expression. This is something which will come in MATLAB, and I'll show you the code which does that. Okay, and then as I said, you could also write the Jacobian of point P, or if you want to find the velocity of P. In this case, there's no real use of velocity of point P, but if you want to write the velocity of point P, all you need to do is write down Vp is Jp Q dot, and Jp is basically dxp d theta 1, dxp d theta 2, dyp d theta 1, dyp d theta 2 times theta 1 dot theta 2 dot. Okay, so let me show you how easy this is to code. It's more work to write this in this form, but easier to code. Switch. Here I've actually done some work previously. This is something which we wrote down earlier, and first part is, well, first we define all the symbolic variables, in the case theta 1, theta 2, c1, c2, and so on. I've defined the position of G1, which I wrote down here some time back. So this part has been done by me on paper, but what part is new is basically finding the Jacobian, and that's super easy. As you can see, it's basically writing the x y position of point G1, theta 1, theta 2, and the x position of g2 theta 1 theta 2. That's all to it. So let's run this, and then you have basically Jacobian of g1, which is something I wrote down, and this one is pretty lengthy, but that's where it comes from. If you want to find the velocity, finding the velocity, then as I said, this is not very hard. I need to create a new variable. Let's call it omega 1, omega 2 real, and then to find the velocity of g1, it's going to be what? It's going to be jg1 times, let me define q dot. Q dot will be omega 1, omega 2. So that should be simply q dot. That's all I need, right? So let me run this. So that's the velocity of g1, which is the same as what I got earlier. And then I can repeat the same thing for bg2. Simply this. So pretty lengthy, but it's super easy in terms of formulas. Okay, any questions? Okay, so let's see. Okay, what I'm going to do is I'm going to actually do the last application of Jacobian, and then we'll take. And that is basically the second one is called to find static forces. Okay, and so before I do this, I'll be quickly go through the derivation. Okay, so imagine a body, if you like, it's pinned somewhere. There are torques acting on it. There are forces acting on it, and so on. Okay, so what we do is, the way this derivation goes is, we assume that these torques lead to a virtual rotation. Okay, when I say virtual, it means that the rotation is fictitious, not real. Okay, and so that the work done in that process is torque. This is basically each torque, which is written as an array, times the rotation, right? And since I want it to be a scalar, I do this thing, which is torque transpose times d theta, which basically means that if I have m torques, then it will be 1 cross m times 1 cross m, because I took the transpose, and then m cross 1, because each of those torques will produce virtual displacement of d theta 1 theta 2. So when I take the product, it will be 1 comma 1, and work done, as you know, is a scalar, it's not a vector. Okay, so that's why it is written this weird way. Now these forces also produce a virtual displacement of dr. Okay, so again, f, take the transpose, and 2 times dr. Again, the same reasoning for why I wrote f transpose dr. And this forces should be such that they actually do negative work. Okay, now because all this is the work done, because all this work is fictitious, there's no real work, I can say that the net work done is 0, because I just created that work, it's not really real. And so then if that work is 0, then torque d theta minus f transpose dr should be 0. So now I can move things around. Okay, let me move the d theta down. So torque transpose equals f transpose dr d theta, but that dr d theta is the same as the Jacobian, right? Remember that Jacobian is basically telling you, in this case, is the derivative of the position with respect to the degrees of freedom. Okay, so we have torque transpose is f transpose j, and because I don't like it to be, because I have this F transpose, T transpose, I want to have F and tau, I'm just take transpose on both sides. Transpose on both sides, which is the right thing to do. So then I have torque transpose of transpose equals F transpose J, the whole transpose. And the transpose of transpose is the same variable, which is torque. And then something to remember is when you have A, B transpose, if you want to split the transpose into the two terms, the matrices A and B, then it's B transpose, A transpose. This is like a fundamental law of taking the transpose. So here I need to do the same thing. So J transpose F, because you have F transpose of transpose, you have F. And so the formula which I was after was the torque is J transpose times F. So really simple formula, but a little bit of things to do to get to that. Okay, so why is this formula useful? I'll illustrate this formula just by showing an example. Okay, so let's pull up the pendulum I drew. Copy. Okay, paste. So the question is, so this is under gravity. Assume that it's stationary. Find the torques tau 1 and tau 2 needed at, let's call this O and P such that the pendulum is in static equilibrium. Okay, so what's the torque needed so that the pendulum is sticking out at angles theta 1, theta 2? Now this problem can normally be done using free body diagrams and then resolving forces and so on, but you could also do it using the formula I just wrote down, which states that the net torque is J transpose F. And when I say this formula is valid, it's valid for any point. So in this case, if I want to find valid for the whole mechanism. So in this case, if I want to find the torque, you can see that there are two places where there are forces. There's a place where the force is on the center of mass here, M2G, and then there is another force at M1G. And there's another force here, M1G. Okay, so in this case, what you need to do is you need to find all the places where there are linear forces, because this F signifies all the linear forces. This torque signifies all the rotational moments. So we have the Jacobian of G1 transpose times the force at G1. The force at G1 is, you know what, let me just write it down this way. It's much clearer. JG1 transpose times FG1 plus JG2 transpose FG2. Okay, so now I can write the force at G1. So the G1, there are two forces. There's one in the X direction, one in the Y direction. The force in the X direction is simply 0. The force in the Y direction is minus M1G, because our notation says that downwards is negative. And then we have JG2 transpose 0 minus M2G. Okay, so what remains is I need to write JG1 and JG2, and then I just need to expand it out. Okay, so that's tau 1, tau 2. Let me see. Should I write it down? We just write it down. So the first term is going to be, and this is basically using the MATLAB code I just wrote down. So remember that the Jacobian was C1 cos theta 1, C1 sin theta 1 down, 0, 0. But here I want the transpose of this. So the transpose of that is going to be C1 sine theta 1, 0, 0. That's the first part. And then the second part is fairly long. It's basically something like this. C2 cosine theta 1 plus theta 2 plus L cosine theta 1, C2 sine theta 1 plus theta 2 plus L sine theta 1, and then C2 cosine theta 1 plus theta 2, C2 sine theta 1 plus theta 2, and then 0 minus m1g. And then if you expand this out, you finally get minus m1g c1 sine theta 1 minus m2g c2 sine theta 1 plus theta 2 minus m2gl sine theta 2, or sorry, sine theta 1. And then the second row is m2g c2 sine theta 1 plus theta 2. Okay, this is more work to write it on paper, but it's much easier if you use the symbolic toolbox, use the Jacobian formula. Essentially, you'll be putting this and that in the Jacobians I derived.